This talk is practice for a presentation that will be given to the Department of Particle and Fields annual meeting on July 14th at 4:45. It's a 15-minute talk, and it'll be followed by a second talk on massless neutrino oscillation. What we're going to cover now is the vacuum wave function and geometric quantization. And wave function interactions is modeled by the geometric product, the resulting geometric scattering matrix, and then physical manifestation by introducing a coupling constant, and the electromagnetic scattering matrix. So the claim we make is that geometric algebra is a universal language for mathematical physics. Clifford's intent in inventing it was to have an algebra of geometric objects. The paper that he presented this in was published in 1878, and he died in 1879, an untimely early death. So the algebra lost the math more with vector algebra of heavy size in Gibbs, and without geometric algebra, which is the natural language of general relativity, the artifice of curved space was used as a calculational tool. In geometric algebra, general relativity can be modeled in flat Minkowski spacetime, where it's phase shifts. That's the analog of curved space, is quantum phase shifts. In absent geometric algebra, Dirac discovered not the intuitive geometric representation, but the unintuitive matrix representation. So it was rediscovered and extended by Hestinus and the Cambridge group and many others from 1965 on. In the algebra, we want to be able to add, subtract, multiply, and divide. Divide is one of the difficult aspects of it. It's essential for invertibility, which you need for singularities, topology, dark matter, topological duality, and string theory. There's only 4 division algebras: real, complex. Real is 1 degree of freedom, complex 2, quaternion 4, and octonion 8. In the octonion algebra, the Pauli matrices are basis vectors in 3D space and Dirac in 4D space-time. So this is the natural vacuum wave function, and it's the same at all scales, from Planck length to Compton wavelength to the boundary of the observable universe. The 1966 version and the 2015 version are basically the same in terms of the text, and which can be found at this link. In the 2015 version, Hestinus added a preference. And in the preference, one of the things he dwelled upon was the need to make bold and explicit claims. I think his experience of having 50 years passed between the first 2 editions and for the geometric representation to remain outside the mainstream is part of what makes him assert the importance of this. So this is what we do. We're making some bold and explicit claims here. This is the abstract that was accepted by the Division of Particles and Fields, and it ends with this statement here, that the model's naturally gauge invariant, finite, confined, asymptotically free, background independent, and contains the 4 forces, and it's finite without renormalization. So one could make considerable additional claims. I hesitated to do that in the abstract because if you make too many outrageous claims, then folks think you're a crackpot. But the model does explain unstable particle lifetimes. You can do branching calculations, branching ratio calculations with it. It contains dark matter and dark energy. The Big Bang, it has an explanation for inflation, and perhaps most important of all, it resolves a lot of the issues in quantum interpretations. We've had almost a century now, starting with the Copenhagen interpretation of various perspectives on the wave function. But by starting with the wave function in the model, I think we resolved pretty much all of those. So the theoretical minimum contains three assumptions. The geometry, fields, and mass gap. For geometry, we take point, line, plane, and volume elements. So this is a form of geometric quantization. These are the quanta. And in the geometric representation, it's one scalar, three vectors for the three orientational degrees of freedom, three area bivectors, and a volume element, a trivector. This is the vacuum wave function. For physical manifestation, we need a coupling constant, and the four fundamental constants that define the electromagnetic coupling constant permit assigning, the various combinations of them permit assigning uh, topologically and geometrically appropriate flux quanta to the eight wave function components. The mass gap, the metric, we take the Compton wavelength of the electron, the lightest rest mass charged particle, and then we can model interactions with the geometric Clifford product, which both raises and lowers physical dimensions. The raised dimension then is space-time. Actually, it's a six-dimensional phase space because you need independent phases for each of the three orientational degrees of freedom. So we've got three space and three phase, and time is the integral of phase. Time is the same for all three orientational degrees of freedom. There's no free parameters in the model. So we're going to look at the vacuum wave function, the geometric product, and the resulting scattering matrix next. The claim earlier that geometric algebra is the universal language for mathematical physics. This is a pictorial representation of that David Hestenes did. He was awarded the 2002 Oersted Medal by the American Physical Society for reforming the mathematical language of physics. The wedge product that we use in geometric algebra has a dot product and a wedge product. The wedge product increases dimensionality. The dot product reduces dimensionality. So that we have dynamic supersymmetry here. In the interactions, for instance, if we start with two grade 1 vector bosons, and we multiply them together, what comes out is a grade 0 scalar boson and a grade 2 bivector fermion. WZ equals Higgs plus top. Taken together, these four superheavies comprise a minimally complete 2D Clifford algebra, a scalar, two vectors, and a bivector. The sum of the masses of the W and Z is the top. The difference is bottomonium, the dominant decay mode of the superheavies, the tangent of bottomonium. And there's no Higgs here. Whether this is meaningful or not, I don't know. But in any case, it's interesting to me. So the geometric scattering matrix looks like this. The blue background is the even dimensional portions of it, which are the eigenmodes. And the yellow background is the odd dimension, the transition modes. So for instance, we have U1 here, the scalar, scalar plus bivector, scalar plus quad vector, and scalar plus sexta vector. The sexta vector again is in the 6D phase space. So these are flavor, the flavor SU3s, the two flavor SU3s, and here we have the color, the color SU3. So we're now at physical manifestation via the coupling constant in the electromagnetic scattering matrix. So the way we get the physical manifestation, we already have our electric charge quantum. We can define the magnetic charge in terms of the Dirac relation and the magnetic flux quantum, interestingly enough, and this will show up in the neutrino wave function. The magnetic flux quantum is geometrically different, topologically different, but in numerical units, it's the same. So there's topological stuff going on here. This is a trivector, and this is a vector. So these are the additional flux quanta that one can define. I'm not going to discuss them in detail at this point. And this is what it looks like. Here now we've taken away the three orientational degrees of freedom by assigning, we've made them different instead of the same by assigning electric and magnetic fields. So this thing ends up being 10 degrees of freedom instead of 8, the 10 degrees of string theory. And on the following slide, we're just really briefly going to look at some of these modes, two-body modes that have been plotted in an impedance network. So impedance governs the amplitude and phase of energy transmission, and impedances have to be matched for energy to flow. And as you can see, here we have the coherence lengths, the particle lifetimes multiplied by speed of light. So for instance, here, the pion, we have these nodes here where the impedances are matched, and we can calculate the branching ratios of the pion and the eta and the eta prime from looking at impedance matching at these nodes. But this explains the unstable particle lifetimes in the sense that they're structured in powers of the fine structure constant because the impedance network is structured in powers of the fine structure constant. There's a lot that can be said about this plot here, but I think I've used up the time I have available to me here pretty much. I want to get one more thing into this, which is the origin of mass. So when we take these flux quanta, if we confine them to the Compton wavelength of the electron, then we have the composite of the electron and positron mass. There's factors of 2 floating around in this. This should be 0.511 MeV, and I still don't understand where all the factors of 2 are coming from. But in any case, this is the origin of mass for the electron in the inertial mass, which is in the electromagnetic fields. Mass equals energy, as we know from Einstein. And I'm not going to dwell on either of these for the moment or any of this. We'll get into this a little bit later. So the next talk is going to be about massless neutrino oscillation. And thank you very much for listening to this.